Hello and welcome. In this video, I'll be covering sections 6.5 and 6.6, which essentially are applications of the unit circle and how they can help us determine the graphs of the 6 trigonometric functions. So the main goals of this video you can see on the screen here, but ultimately being able to, if I gave you coordinates on the unit circle, be able to figure out what it would be in other quadrants by either reflecting over the x, the y, or the origin. Also being able to determine any of the values for a specific angle, so either sine, cosine, tangent, secant, cosecant, and cotangent for any of the angles that are on the unit circle, and then also being able to utilize those to make a graph. Now we'll also talk a little bit about how we can utilize a calculator to determine some function values for numbers that maybe are not on the unit circle, but ultimately that's just going to be a matter of making sure that we're in the correct mode and can type things in correctly. But that is essentially what this video will be about. Now, just as a quick review, last lesson we did discuss what the unit circle was, essentially the circle that's centered at the origin with the radius of 1 that has that equation x squared plus y squared equals 1. So now we're actually going to talk about what each of those things represents that we wrote on the unit circle, so try and make a little more sense of why we even did any of those things. So for each of those angles that were provided, so all of the central angles are essentially going to be the thetas in this formula here, but any x-coordinate on those points that are actually on the unit circle, those would represent the cosine value for that central angle. All of the y-coordinates would represent the sine, so one way you can remember that is alphabetically x comes before y, so similarly alphabetically cosine would come before sine, just c before s. And then tangent on the outside we technically already labeled, but if you needed to find it or you maybe forgot some of those values when it came to filling out a unit circle, it would just be whatever the y value is divided by whatever the x value is. So you can also think of tangent as it's a sine over a cosine when it comes down to it. Now, as far as one other strategy we can go with when it comes to being able to have the unit circle memorized, if we can just maybe get the first quadrant taken care of, notice we could technically just reflect over either the x-axis or the y-axis to come up with what the points in the other quadrants would be. So that would be quadrant 2 or quadrant 4. Ultimately, all I would have to do is either switch the x to a negative or potentially the y to a negative. And I could technically also do a reflection about the origin, which would be where I make both the x and the y become negative, or I could just take either the second quadrant or fourth quadrant that we had and reflect it over its corresponding axis to get the third quadrant as well. But ultimately in that bottom left corner, everything would just have a negative sign on it except for the tangent, because after all, the tangent would be the y divided by an x, and if they both are negative, the two negatives would become a positive value. So just another way that we could go about doing the unit circle when it's all said and done. So if we go ahead and maybe see some examples of how we could utilize the unit circle to come up with some of these values. Notice some of these are not necessarily the sine, the cosine, or the tangent. They actually are the reciprocals of some of the functions. So on occasion, I may have to actually take whatever I notice on the unit circle and flip it. And I do 100% understand that unit circle is super, super tiny, but hopefully if you follow along, having maybe one that was filled out in class or one that you've printed off, it might make it a little easier to see exactly what's going on, but I'll just use that kind of as a reference as I work through these problems, just to show you exactly where I'm looking and why I'm writing down the values that I'm writing down. Now also on occasion, some of the angles that maybe are provided are a little bit either too large or too small for the angles that are on the unit circle, so we can still take advantage of the idea of being coterminal, which, remember, that just means I can add or subtract either 360 or 2 pi to any angle, and it technically doesn't change its location, but it would change the value of the angle technically. So we could still use that to our advantage when it comes down to it, which hopefully as we work through these examples you'll kind of see what I mean by that. But anyway, if we go ahead and look at this first one, it says I want to figure out what tangent of pi thirds is. So first I would identify the the pi thirds angle, which should be that steep one in the first quadrant. Again, the more you practice it, the easier it is for your eyes to kind of get drawn into the correct area, but in this case it would be all of the pi thirds are close to the y-axis, so that's where I would start looking. In this case, the numerator having a 1 as the coefficient on the pi kind of tells us for sure we're going to be in the first quadrant, so I didn't have to go too far to identify that. But ultimately at that point I would just look to see what is the tangent that's been identified, and if you had it large enough it would just be that number that's on the outside, which is a rad 3, so tangent of pi thirds is rad 3. And as we work through these, hopefully this becomes significantly faster for you to be able to do than all of the description I just went through. So I'll probably speed up a good majority of these. Hopefully we can follow along as we go. If not, pause, rewind, and maybe try and listen to the description a little bit more closely. But anyway, if we go through the next one, cosine of 3 pi fourths. 3 pi fourths would be this one in the middle. The x value at that would be rad 2 over 2 with a negative sign on it, so it's just going to be altogether negative rad 2 over 2. Letter C here, negative pi 6, we could picture as it's going down pi 6, if I get rid of that other reference. Since it is a negative angle, it would just be going the other direction pi 6, or what I could do is just add 2 pi to that value, and notice that that would be the exact same as doing sine of, and if I made 2 pi have a common denominator, that would really be like 12 pi 6, and 12 pi 6 plus negative 1 pi 6, so that would equal 11 pi 6, which is, again, essentially the same location. It's a weird looking 6, my bad. But it would be the same location as what we had here. It just would be going all the way around. But I still, because it's sine, will look at what the y value is, and the y value at that happens to be a negative 1/2. Anyway, let's go ahead and continue on. The next one, 4 pi thirds. If I go ahead and get rid of my references on that unit circle, 4 pi thirds would be the one in the third quadrant. I'm looking for the cosine value, so that would be the x-coordinate, and the x-coordinate for that one is, in fact, negative 1/2. Cotangent of pi, this is the first reciprocal one. I still start by going to where is pi, that's the left side of the x-axis. And if we look at what's there, I need to figure out what the cotangent is, so that means I need to figure out the tangent first, which happens to be 0, and then I flip it. So if we think about what that would turn into, I could kind of picture like 0 is like 0 over any number. I just chose 1. So if I flip it, it would become 1 over 0, which kind of the moral of the story here is anytime you take a value of 0 and find its reciprocal, it will become undefined, and it actually will work the exact opposite as well. The reciprocal of undefined will turn into 0. So just kind of keep that in mind when it comes down to it. Most of the other ones, if I needed to flip it, are a little bit easier because they don't get an undefined value. You actually just get a different value altogether. But remember, 0 flipped is undefined, and undefined flipped becomes 0. Anywho, let's go ahead and continue on. The next angle, as we can see, negative 7 pi halves. That's definitely not on the unit circle. So what I could do is just add as many 2 pi's as I could think. So in this case, if I added 2 pi repeatedly, 2 pi in this case would be like 4 pi halves. So if I added 2 of those 2 pi's, or 4 pi halves, that should take me up by 8 pi halves, which actually brings me up to a positive pi half. So negative 7 pi halves, if I were to go around that many times, technically would be the same as doing positive 1 pi half. So ultimately I'd be focusing my attention on this angle right here, and if I think about what is cosecant, cosecant's the reciprocal of sine, so I look for the y value. The y value there is 1, and 1, if I flip it, happens to stay 1. So I'm going to go ahead and just start boxing these up because I am going to get a little, I don't know, clustered here with the bottom part of this, but we'll go ahead and continue on. Again, now 225 degrees, that would just be in this third quadrant. I need the y value there, so the y value happens to be negative rad 2 over 2, so that would be the sine value for that angle. 330, if we reference that one, that would be this one in the fourth quadrant. And if I need secant, that's going to be the reciprocal of the cosine, so it's going to be take the cosine value and flip it. Well, if the cosine is rad 3 over 2, if I flip that, that would become 2 over rad 3, which would be something I need to rationalize. And all I'd have to do is multiply top and bottom by the square root of 3, and we would end up with 2 square root of 3 over a regular 3 when it's all said and done. The last two here, if I go ahead and look at the angles, the 780, that would just be too large, so instead of adding rotations, this time I'm going to take away rotations. And it looks like in this case, if I take away 2 360s, which really is like subtracting 720, that would give me a different value that I could still utilize that's on the unit circle. And if we do that, if I subtract 720 from that, that gives me 60 degrees. And so now I just need to reference that 60-degree angle, which happens to have a tangent that equals square root of 3. And then the last one, negative 1260, I'll probably end up needing to add, I think, 4 360s. And we can go ahead and maybe bring a calculator into that just to kind of show potentially the math behind this. You could also just do repeated addition with 360 until you finally get an angle that works. So notice all I did was just keep the answer plus 360, and now I should just be able to press enter over and over until I finally get a positive angle. First positive it looks like I got to was in fact 180, so if I go ahead and switch back here, This is going to be the same as doing the cosecant of 180 degrees, which should be the left side of the x-axis again. So cosecant is the y value. Since the y value is 0, again, just like before, 0, if I flip it, will become an undefined value. So the cosecant of negative 1,260 should be undefined. Now again, all of those questions on the previous slide were all things that were from the unit circle. So what if I had some angles that maybe were not on the unit circle? Ultimately, what I could do is just bring a calculator into the problem and figure out what their approximate value is, because after all, it would give me a decimal value that I'd likely have to round, so it would become an approximation. But ultimately with these, I would just need to be very mindful of what measurement the angle is being provided in, so whether it's in radians or degrees, and I have to then make sure that the mode the calculator is in matches the type of angle we're discussing. So for this example, I'm just going to go with whatever letter A is and then try and identify all of the other ones that are in the same mode. So if we look at letter A, it says cosine of 2 pi fifths. I don't see a degree sign, so that basically just means I'll need to be in radians for this example. If we look at letter B, tangent of negative 3, I don't see, again, a degree sign, so that one must also be in radians. Letter C does have a degree sign, so I know I need to be in degree mode for that one. Same thing with letter D, it is negative 62 degrees, so I'll have to be in degrees. Letter E, no more degree sign, negative pi or 5 pi ninths, that's going to be a radian again. And then the last one, I see a degree sign, so it would be degree. So basically the easiest way to tell what mode you should be in is if you see a degree sign, make sure it says degree at the top of your calculator screen. And if you don't, make sure it says radian at the top. So I'm going to go ahead and just pick a mode and answer the ones that are in there. So if I bring up the calculator, it looks like I'm in degree mode already. So if I go ahead and switch back, let's just do the first one, sine of 173 degrees. So just be sine 173, press enter, and it gives us our value. I think this said in the instructions around 4 decimal places, so 1219 it looks like, so 0.1219. Next one, cosecant. This will be a little bit trickier, this bottom row where it's all the reciprocals. The typing in on a calculator, I just have to do 1 divided by whichever its reciprocal is, so cosecant goes with sine. So this will essentially just turn into 1 divided by sine of the angle, negative 62 degrees. Close the parenthesis, press enter, and it gives me negative 1.1326-ish. So negative 1.1, what was it, 326. And then the last one in degrees looks like was letter F, so I'll go ahead and do that one. It's cotangent, so I'll need to type in tangent and then flip it. So basically just do 1 divided by the tangent and 471 degrees. So 1 divided by tangent, 471. Press enter, and it gives me negative 0.3839. Negative 0.3839. So there's my 3 ratios that were in degrees. Now to show how I would switch back out on the calculator, I would just press mode, which is the button right next to the second feature. I would go down to where it says radian, press enter, and then just quit back out, or you can press clear, I believe, and that would also take you back to your main screen. And now I should be able to type in anything I need to. So for this one, the first one was cosine of 2 pi fifths. So cosine 2, and then pi, if you haven't found it yet, is the second function of the power or the caret button. And then I just do divide by 5. If you wanted to use the fraction template, you can, but you don't necessarily have to because it's just going to convert it to a decimal anyway. So for this one, 0.3090, so basically just 0.309. 309, not 039. Okay, the next one, tangent of negative 3. Again, kind of a common misconception here is you don't have to have pi in order to be radians. It could just be a whole number like this one, so or at least an integer, I guess, because it has a negative sign, but tangent of negative 3 would give us that value, so 0.1425. 1425. And then the last one, secant, again, just more practice with the idea of how do I do these reciprocal functions. I basically just type in 1 divided by to start it, and then whatever secant goes with. In this case, secant goes with cosine, and it was negative 5 pi ninths. And just type in the negative 5 pi divided by 9. Close the parenthesis, not that it really matters a whole lot. You could actually do it without closing the parenthesis, and it still evaluates it correctly. But this one, negative 5.7588. Negative, I already forgot the number, 5 points. 7, 8. Nope, 7, 5, 8, 8. And there we go. We've got our last three here. Again, the kind of trick with these, especially if you're doing consecutive problems like this, I might recommend doing exactly how I did this, or at least modeled, and just answer all the ones that are in the same mode. That way you don't have to do a whole bunch of switching back and forth. But again, it's extremely important, especially when you bring a calculator involved, to make sure that whatever mode the calculator is in does match, in fact, whatever angle you're trying to plug into any of these trig functions. And another key takeaway here is all the reciprocal functions, secant, cosecant, and cotangent. We just have to type in 1 divided by, and then either sine, cosine, or tangent, whichever one it corresponds best with, to be able to actually compute that value, since we don't actually have secant, cosecant, and cotangent buttons, at least not on the TI-84s. The TI Inspires do have the ability to do that, so you wouldn't have to really do anything all that special other than just make sure you choose the right function inside that trigonometry button or menu that pops up on that calculator. But hopefully this is all so far making sense. All right, so now we're going to move on to one of the bigger concepts of this section, or these two sections really, which is the idea of how do I draw the graphs of each of these trig functions. So if we think about the unit circle and just some of the nice values, if you really break it down or look at it pretty closely, if I had you look at all of the x's and y's and just pick the ones that are going to be nice points to plot, I think we would all probably come to this same conclusion of plotting anything that's a 1, a 0, or a -1 would likely be the nicest numbers to actually plot. Now 1/2 paired with something might not be too terrible, but again, that would still be, because it's a decimal, not necessarily the most accurate when it comes to graphing. So kind of the key takeaway here is when it comes to a graph, usually we're just going to start at whatever happens when the value is 0. So if we think about where is the value 0, well, that really would just be the positive side of the x-axis if we think about it this in a unit circle sense. So if I start there, we know that the x value, as mentioned earlier, should be the cosine. So cosine technically should start at a high point, or its highest value, 1. Whereas sine, as you can see on the screen, this sine wave is being shown. The sine is the y value, and it actually starts at 0, hence why graphically you notice this actually starts at the origin. So kind of a key takeaway here is most sine graphs, unless it's been shifted in some way, shape, or form, which we'll talk about that a little bit more here in a little bit, but the sine function normally should just start at the origin, unless, again, there has been some form of vertical or horizontal, which is actually called a phase shift for this particular function. So if you saw addition or subtraction, that point might move, but if you don't see any addition or subtraction, there's 100% confidence of sine must start at the origin. From there, if we think about what's going to happen, well, if I go through the first quadrant, if I go through all those kind of ugly numbers, the 1/2, the rad 2/2, the rad 3/2s, at least for the y values, the cosine or the x values go the exact reverse. They go rad 3/2, followed by rad 2/2, followed by 1/2, then 2, 0. But again, if we just kind of think like, you know what, I know I'm going to cycle through those, but I don't necessarily have to plot those points because they're not very accurate anyway. We could just think like, well, if I just go a quarter of whatever the rotation is, so the rotation in this case we're going to talk about is what's called a period. And again, I'll dive in a little bit more. So as you can see on this visual here, one full period, if I were to maybe try and make this stand out a little bit, one period is actually how long it takes to complete one full wave. So that would be from start to finish. As we can see on the x-axis here, that would be a value of 2 pi, at least for the sine and cosine graphs. And ultimately that's because it takes all the way around the unit circle for it to be able to start repeating the values, which is the idea of being periodic, hence why that's called a period. But in this case, we're going to go ahead and just take advantage of every time I go 1/4 of a rotation or 1/4 of whatever that period is, it will go from a nice number to another nice number. It just happens to either go from 0 to 1, back to 0, back to -1, back to 0, back to 1, and so on and so forth if I just keep going around and around and around. Or if I started talking about the x values or the cosine would start at a 1 or a high point and then go to 0, then -1, then 0, then +1, then 0, then -1, and so on and so forth. It just keeps repeating through those same things. And visually speaking, I hope you can kind of see, like, as I increase the angle on the x-axis, the point I would plot will just kind of keep cycling between something that's either on that midline. So the midline really is this line that kind of is cutting the wave perfectly in half. So for this example that you can see it's the x-axis that would be cutting in half. And then ultimately every quarter of a period, so in this case if we just went 1, 2, 3, 4 and wrote whatever that period is, in this case there was no stretching or shrinking, so it stayed 2 pi. If I just cut that into a quarter, each quarter point, notice it either goes from a 0 to a high or maybe a 0 to a low back to a 0, and it just continues that same pattern, and it would technically continue on and on to the right as well as on and on to the left. I just have on this particular slide just one of them drawn, but technically it is, again, I can go forever in the negative direction or positive direction as an angle because we can continue to repeat. It just keeps making the same shape over and over and over. So I'm just kind of displaying for notes purposes just what one cycle would look like. And as we work through hopefully a few examples, that'll start to kind of sink in. But at this point, I'm going to guess majority of those watching this video are probably a little bit confused, but I promise eventually it will kind of all come together. So as I'm talking about this, may as well kind of talk about, because we said, well, the sines are the y values and they would cycle through the points like this. If I scroll to the next slide really quick, the cosine graph, you can kind of picture the same general idea. Again, if we kind of picture what those points would be, if I go 1/4 of a rotation around, the x value here would be a 1, then a 0, then a -1, then a 0, then back to a +1. So every time I go 1/4 of the way around, which again, that's the idea of a period. If there was some sort of multiplication or division, that might get stretched out or maybe compressed down, but still the idea of how far apart are those things being separated by, well, it should just be 1/4 of whatever the period is. So when it comes to labeling axes, usually it's just going to be put 4 tick marks, and whatever that 4th tick mark is, which in this case you can kind of see the 4th tick mark has been labeled as 2 pi, that actually does happen to match what the period of sine or cosine should always be, because it does take one full rotation to get around. Now for this specific function, notice it actually started with a value of 1, so instead of it starting at the origin, it actually started at a high point. So my first point I would plot for cosine would be that high point, and then from there, every quarter of the period away, it just goes through kind of that same pattern of just what's next in the sequence. Well, if I'm at a high, the next thing I'd have to go through is a 0 or a mid. Something that's on the midline is probably more appropriate to call that a mid in case there was a vertical shift, because it won't necessarily always be on an x-axis, but for this specific example you can see that it would be a 0, and then after that it would go to a low spot, because that would be at -1 next, and then back to 0 after that, so back to the midline or the x-axis, and then the last step would be back where I started, which is where 1 is. So again, generally speaking, that idea of that visual of wherever it takes or however long it takes for it to start cycling through everything again, that is the idea of being one full period, which again is 2 pi for both sine and cosine, unless there's been some sort of stretching or shrinking. All right, now if we go ahead and jump into like what would tangent look like. Again, this is just going to be, I'm going to kind of talk about why the shape of the graphs are what they are, and then I'll dive a little bit deeper into how do I actually make the graphs happen, and hopefully you can kind of recognize the patterns that happen with this one. But tangent, what's a little bit peculiar with it is that we actually want to kind of go and think in terms of like this would be like -90 degrees, or in radians -π½ and +π². Ultimately, why we would want to do that is that's actually where on the unit circle, if you look at the tangent values, those two things are the first kind of consecutive ones that are undefined. And again, I don't want to picture that like it's 3π², because, well, 3π² doesn't come before π². So I kind of want to picture like I'm starting at the bottom of the unit circle and I'm working my way up to make that first cycle. I just will have to plot a few negative angles before I can get into the positive angles. And ultimately, halfway in between there, that tangent value at 0 is in fact 0. And then the other nice tangents are the ones that are perfectly in the middle of the first and fourth quadrants, where it's either a +1 or a -1. So to kind of give you an idea of where each of these things lie, the undefined values essentially will be like the first and last parts of the period. So those would be vertical asymptotes. If you think back to how we graph something that's undefined, that's more of like a connection with rational functions from earlier in the year. But an undefined value should graphically come back as a vertical asymptote. And then in between there, I would just kind of think, well, exactly halfway is this value 0, so halfway between those two vertical asymptotes should be 0. Ultimately, for tangent, you can also just think, I know it's always going to have 0 as the first point that I could plot, and then one period later it would also be a 0, another period later it would be a 0 again, and so on and so forth, and we could plot those points accordingly. Obviously, this is just showing one wave, but maybe if I use the picture underneath it, we'd plot our first 0 here, and then plot the next one, which is whatever that period is away, to get the next 0. In this scenario for sine and, in comparison to sine and cosine, sine and cosine actually take all the way around the unit circle to repeat. Notice here it actually only takes half, because if I go to the next rotation here, next sequence there, notice I actually go through the same order. If I were to follow it, I'd go undefined to -1 to 0 to +1 to undefined again, and then repeat. So instead of it taking all the way around the unit circle, now it actually only takes halfway around, which is actually why you can see here in the notes that the period for tangent, this will also be true for its reciprocal cotangent, but we'll dive into that in a second. But the tangent and cotangent functions, generically speaking, should have a period of pi instead of 2 pi, like sine and cosine and secant and cosecant would all have. So it just takes a little bit less time for it to cycle through all of the key points. Now, if we go ahead and look at what else happens, halfway between the 0 and the undefined value is this nice value 1. So notice if I go about halfway in between, I actually end up plotting something that would be a nice value on the y-coordinate, which would be whatever number actually is in front of this, which we'll talk about a little bit more. But for this one, having no number in front, so there's no vertical stretch, the value of 1 for the y would stay a value 1. Not that you have to plot all these other ones, but we could technically utilize rad 3 over 3 and rad 3 from the unit circle if I really wanted to do the 30-degree angle or the 60-degree angle, or pi sixth and pi thirds accordingly, since we're talking radians for this visual. You could picture where those would be, but again, why use decimals that are ugly? Let's just try and stick with the nice numbers. 0 and 1 and -1 are kind of that nice trio from the unit circle. So anyway, generically speaking here, I'm going to go ahead and just kind of mention, like, okay, if I have my two vertical asymptotes, I would then draw those 3 points in the middle. So it'd be like halfway in between, I'd go up to whatever 1 is. Halfway in between here, I'd go to whatever -1 is, and just make sure that the tangent function always comes up the page unless it's been reflected upside down. So again, all of the notes here, you can kind of see, like, here's all the key info about the function, but multiple, like, I'm hoping again when we get to actually seeing some physical examples of this, that it will start to kind of sink in, like, what's the easiest way to make these graphs happen. And really it's just a lot of taking advantage of being a specific period away from each other, so I can plot all of the same things. So the asymptotes would all be separated by the same amount, the zeros would all be separated by the same amount, the high points, like the over to the right and then up from the 0, those all would be the same distance away. So you can kind of see that there's some patterns happening here because of the idea of being periodic, but yeah, I probably am just more confusing than I am helping right now. But the examples, when we work through it, hopefully will make sense. If not, just come find me and we can talk it out face-to-face or one-on-one, whatever is easiest, and gonna get things figured out at that point. All right, so we'll talk about the other 3, the reciprocals of the other ones, but ultimately most of my focus is going to be on those original 3, sine, cosine, and tangent. Now, SOHCAHTOA, the ones that we've had more experience with. The secant, the cosecant, and cotangent, again, are just reciprocals of them. So if I can graph the first 3, really when it comes to graphing secant and cosecant, I plot the exact same points. It's just how I interpret them that's going to be a little bit different. So as you can see with this visual here, in the middle here, it's showing the sine wave, so I'd plot all the same points as if it were just a sine function instead of saying cosecant. It's just a matter of what happens to those values. Anytime that sine would equal 0, notice again, this kind of comes back to an earlier part in this video, is if I take 0 and find its reciprocal actually becomes undefined. So kind of the shortcut for secant and cosecant both is wherever the original function, either sine or cosine, is equal to 0, that's actually where I will draw vertical asymptotes for its reciprocal function, so either secant or cosecant. Here we have the visual for cosecant, which is why we would think of the points for sine, but instead of drawing the actual wave like this has in the middle, in fact what I have highlighted there in yellow, we wouldn't want to draw. We'd actually only physically want to draw this outside part, where it's, notice it's upside down U's at all the low points and right side up U's at all the high points. And then I would just pay attention to be a little bit more careful to not cross over any of those vertical asymptotes. So I just wanted to kind of focus, like, this part that's in orange really is the actual graph for the cosecant. So you can kind of picture it. It's like the wave that we know sine or cosine would be. It's just kind of flipped inside out. So instead of it going towards each other and being connected, now it's actually disjointed or not connected and actually going away from each other. So not going towards the midline, but actually away from the midline. And if I really quickly just scroll to the next one for what secant would look like, notice again we would just think, what is the cosine function? What would all the points be for that? So it started a high point and then just kind of go to a mid, back to a low, back to a mid, back to a high, back to a mid, and so on and so forth. It would just keep repeating through those. But again, all the places where it was 0 or wherever the midline points would have been, those now just turn into undefined values, so vertical asymptotes. And then from there I would go ahead and draw all of my u's at all the high points, like those, and then all of the upside down u's at all the low points, just again taking care to make sure I don't cross over those vertical asymptotes, but also making sure that I kind of leave that open space in the middle where sine or cosine would have existed. And if I scroll on to the last one, cotangent, really the only difference with cotangent is wherever tangent was 0, it would become undefined. So since tangent normally was 0 at the origin, that would then become an undefined value. So ultimately now we would just take advantage of, well, every pi later, so this would be like pi here, because that's halfway between 1 pi half and 3 pi halves. That would be 2 pi halves, which is pi. But notice I would end up having a vertical asymptote every single pi, because again, that is the period for both tangent or cotangent. So that's where the next thing that should be identical would be. Halfway between those happens to be zeros, so that's where the x-intercepts would be plotted, and then halfway in between those, I either go up whatever the a value is, which is going to be the number in front of the function, or down whatever that value is. And cotangent ultimately just needs to come down the page, whereas tangent's the one that's supposed to come up the page. So you can kind of just picture like tangent, if I flip it, really looks like a cotangent. I just know that it also is kind of like it's been shifted a little bit to the right. And the main reason being is the tangent graph technically would have been undefined here at pi halves. And as mentioned again earlier in this video, if I took undefined values and found their reciprocals, they actually turn back into zeros, which is why that's actually an x-intercept now instead of still being undefined. All right, so far I'm going to guess I've pretty much thoroughly confused you, because that was just a whole bunch of information without a whole lot of applications being seen. But hopefully we got all the kind of key things out, so where now when we start talking about it, we can kind of make connections with some of the things I've said prior. Now, all of these things that we've talked about, again, we can say are periodic because they do have a repeating pattern. Sine and cosine were the waves, secant and cosecant were the u's and upside down u's, and then the tangents were the semi, I mean, they look like a cubic shape, but they're technically not cubic. But in appearance, again, they just repeated the exact same thing over and over and over. Now, all 6 of those, again, as just mentioned, they're all periodic, and it's the how long it takes for it to do that repetition that we actually call or use the phrase, it's the period of that function. So sine, cosine, secant, and cosecant, all 4 of these bad boys, notice they all should take a full rotation around the unit circle. Again, if it was condensed down, which we'll talk about, or compressed or shrink, I think are some of the other words that we have from our past, or maybe stretch. If that has been stretched horizontally in some way, shape, or form, that might change, but generally speaking, we should say sine, cosine, secant, and cosecant, since they're all related to one another, should have a value of 2 pi unless it's been stretched or shrink. Tangent and cotangent, on the other hand, the other 2 are ones that actually only take half as long, so they only take pi or 180 degrees to rotate through all of their things before they start repeating. Now, the sine and cosine graphs have a thing that we can represent that's called an amplitude. The amplitude essentially is, if we think about, okay, I've got an x-axis, and let's just say I thought of a sine graph where it would kind of start at the origin, go up a little bit to a high point, then come back down to a 0, then to a low point, then back to a 0. Ultimately, whatever that distance here between the midline, which is the thing that cuts it perfectly in half, and either a high point or technically I could say to a low point, both of those right here would be called that amplitude. So just to kind of give you a little bit of a visual, if I could fit that word on here, I don't know. But the idea of an amplitude is essentially how far up or down I can go from whatever that midline is. If it helps, you could say double the amplitude is always how far the high point is away from the low point. So if you know that it's a distance 2 to get from high to low, then that means its amplitude must be half of that, or 1. But anyway, that's just some terminology that we have. So again, period is the how long it would take to go one full rotation through all of the points. So for sine and cosine, it's how long it takes to make one full wave. For tangent, it would be how long it takes to make one full cubic looking shape, or how far maybe the asymptotes are away from each other. And then for secant and cosecant, it would be how long it takes for it to make one upside down U and one right side up U. Or you can go from asymptote to, I guess, not the next asymptote, but 2 asymptotes later. That would also be another way we could identify the period visually, at least with secant and cosecant. But generally speaking, again, period is how long it takes for it to start repeating the exact same pattern. All right, so now on to, let's just discuss the first two that are relatively basic, the sine and the cosine graphs. These are the ones that really have the highest presence or application when it comes to like graphs are concerned, or at least connection with other classes. But here I'm going to kind of discuss with some of the older functions that we know, such as like a quadratic or maybe a cubic or any of those other things. We technically have the ability to stretch, compress, shift, or reflect. Those are our 4 main words for transformations. And ultimately it would just kind of come down to where is a number and what would it be doing. So notice if I had a number in this A spot, that would be multiplication outside. That's actually going to stretch it vertically, and that basically means that would affect the how far up or down it goes. So the amplitude is essentially going to be connected with that front number. So whatever the amplitude is, it's always going to be, because it's a distance, a positive number, hence why the absolute value symbol is around it. But if you just think like whatever number I see in front of either sine or cosine, that value A is always going to be how far up or down I go from that midline. The period, on the other hand, right, that would be something that might get affected because I'm talking more angles there, or how far does it take horizontally for it to repeat. Since that's more of a horizontal idea, that's why multiplication inside, in other words, in this spot where B is in either of these cases, whatever's in front of or multiplying your value of x or your variable, could be a theta, I suppose, if you wanted, but most of these are just going to stay x's. It's going to be whatever that number is. I'll take the period that it should be, normally 2 pi, and just divide it by whatever that number is. So in some cases, the b value might actually be a fraction. If the b value is actually a fraction, I would just do that keep flip change idea. So if I had to do like 2 pi and I need to divide it by I don't know, maybe like 3/4, I would basically just keep the 2 pi, flip the 3/4 to make it 4/3, and now go ahead and multiply across, so that would become 8 pi thirds if I needed to do it, just as a random example to kind of see like what if it was a fraction, how would we deal with it. We would just basically flip the fraction that I'm dividing by, change it to multiplication, and if I could reduce, I would. But again, that was just a random example just to try and give you somewhat of a visual of what if there was a fraction in that spot, how would we handle it. And again, that's going to affect how long it takes for it to repeat. So knowing what the amplitude and period are, those two things are kind of the main basis for how we're going to label our axes. Because we don't necessarily, for these, I think you could probably recommend or kind of foreshadow the fact that we aren't going to want to count by just ones on the x and y axis. Because after all, the angles that we'd be plugging in are things like pi thirds, pi fourths, pi fifths, pi sixths, so on and so forth, that it's definitely not going to be nice to count by whole numbers when numbers like pi fourths or pi halves or things like that are involved. We actually will want to just count by whatever a quarter of the period is, because as we said, or as I mentioned earlier, a quarter of the period is how long it takes for it to kind of go from nice number to nice number. Now the other two things that could potentially happen have to deal with shifts, right? So if I notice that I have addition or subtraction in either of those two spots, adding or subtracting inside is really like what we've called in the past a horizontal shift. It just happens to have a slightly different name called a phase shift, just because it's a periodic function. If I shift far enough, it actually just turns into the exact same shape, which all of the other functions we had, that wasn't true. But because this has some repetition, or the shape does get repeated, instead of us calling it a horizontal shift, it's called a phase shift. Honestly, I'm not going to be that picky. If you wanted to just always call it a horizontal shift, that's perfectly fine. Just realize phrasing wise here, it's actually going to say phase shift on any of the questions in the homework, or on your piece of paper, or even on any assessments I'll give you. I'll be asking you to identify a phase shift, so just recognize that that means how far is it horizontally moving. Now you could utilize the formula I have here, where basically if there was subtraction inside, I would have now a negative c value, so the double negatives would cancel each other out. then divided by b would give us a positive, so that would move it to the right. I honestly think it's easier to just think if it has addition on the inside, it's going to go to the left. If it has subtraction on the inside, it's going to go to the right, which that way it's just consistently with or consistent with how we've dealt with other functions, and then you don't really have to worry about this extra negative sign that I have in this formula, so you could technically just drop that and just go whatever the c value is, make it positive, divided by whatever the b value is, keep it positive, and then you don't have to really worry about any of the negative signs. It would just be now, what do I see? Well, if it's addition, I know it's left. If it's subtraction, I know it's right, and just to take advantage of that. But again, I'll just keep it in that form in case you wanted to use it that way. But again, I just wanted to kind of point out that you could also just fall back to what we already have learned and utilized multiple times, which is addition moves things left, subtraction moves things right. The easiest one out of the three, actually it's probably tied with the amplitude, is the idea of vertical shift. Vertical shifts kind of are always going to be the standalone at the end. Whatever you add or subtract on the outside, adding moves something up, subtraction moves something down. So again, whatever that value of d, or that number at the outside part that's being added or subtracted, would essentially account for any vertical shift. So we'll kind of start with, let's maybe do a few examples where all I have to worry about is maybe some stretching or shrinking, maybe potentially a negative sign. If I had a negative sign, ultimately all a negative does, if you think back to it, had this a value had like a negative in front of it, all that would do is reflect something over the x-axis. So you could just kind of think, if I saw a negative there, it would just be upside down, or it would do the exact opposite of what it should do. So instead of going up, maybe for a wave, it would actually start and come down. That would basically be all a reflection would do. So hopefully the follow-up examples I'll work through here in a second will kind of help solidify how each of these numbers, if I had something in that spot, would affect a graph visually. Now you'll notice as I go through and do some of these graphs, I've got a few kind of tips and pointers, I guess, to kind of take note of. I've already mentioned most of this, but the sine function, just again thinking of the unit circle, if you wanted to, you can always just picture, what is this point over here at the far right? Well, that should just be 1, 0. Hopefully we can remember that the sine value would be the y, so notice it should normally just start at the origin unless it's been shifted, and then from there it normally should go up to a max, so you can kind of think that's going to go from a mid to a high, or a 0 to a max is how I have it kind of written here at the bottom, but it will follow a pattern of, once I have kind of that first couple of points, it will go 0 high, 0 low, 0 high, 0 low, 0 high, 0 low, and so on and so forth until I run out of grid both directions. Cosine, on the other hand, at that same angle, right, notice cosine actually starts at 1, so I actually start at a high point, and then from there the only option I would have is to go down to a midline or a 0, so hence why it goes more from a max to a 0. Then next would be a min, because it would go down to a -1, and then back to a 0, and then back to +1, and then back to a 0, and just continue on and on and on. So when it comes to our labeling of our axes, ultimately the x-axis will want to basically account for anything that's horizontal, so that would be like, what's my period, what's my phase shift, and just kind of go out whatever amount would be. I personally like to go whatever the fourth tick mark is, that way each tick mark would be a quarter of the period, and that's basically just to kind of take advantage of the fact that every time I go through a quadrant, it goes from a nice number to the next nice number, 0 to 1, or maybe 0 to -1, or vice versa, 1 to 0 or -1 to 0. But I skip over all of those numbers if I actually skip everything in the quadrant, hence why I would want to either go 4 units out or maybe just some multiple of 4 in case I needed to have a phase shift that was even smaller than whatever that quarter of period happened to be. The y-axis, generally speaking, is usually easier to label. It's just going to be what is my amplitude and what maybe is my vertical shift, and just make sure that I count by numbers that kind of help me easily identify each of those. So if I had like a vertical shift of 2 and an amplitude of 3, I'd probably just want to, on my grid, just count by 1s. That way I can account for both of those values. Counting by 2s would make the amplitude of 3 a little bit tougher to do, but let's say maybe my amplitude was like 20 and I had a vertical shift of 5, that might make more sense to count by 5s instead. That way I can still account for both numbers relatively easy. Now pattern-wise, it ultimately comes down to like, what's my first point that I'm going to plot, and then from there it's going to be what has to be next in the sequence. So usually it's going to, again, go max 0, min 0, max 0, min 0, or you can also think of it high, mid, low, mid, high, mid, low, mid, and so on and so forth. It's just a matter of what's that first one that I do and what do I go from there that's going to change from problem to problem depending on if it's a sine or a cosine graph, as well as if I have a negative sign or not in front that maybe has reflected it upside down. So again, hopefully the next 3 or 4 examples that I'll work through will help solidify this concept, but if there are still follow-up questions afterwards, please just don't hesitate, come find me, and we can work through a few kind of one-on-one and hopefully solidify it at that point. All right, so finally some examples to work through. So let's go ahead and identify some of the key things that we notice. Notice this is not just a basic y equals sine of x, which would be something where there was no stretching or shrinking. It would be the same as the graph that I kind of presented earlier in this video. This one now is being stretched vertically because of that 3, so that's going to have an amplitude of 3. And then I also have multiplication inside, so that's going to either stretch or compress the period. So my period in this case will likely become something other than 2 pi. And from the previous slide, or 2 previous slides ago, I guess it was, hopefully we can remember that the formula should be 2 pi divided by the b values. So for this one, it would be 2 pi divided by 2, which actually equals just pi. So utilizing how do I kind of make these grids work? Well, for the most part, at least with the worksheets I've provided, I've given you similar grids to what's on the screen right now. For sine and cosine, I actually kind of recommend that you just use every other line. Otherwise, you have to draw quite a few more waves or quite a few more periods, if you will. So kind of expanding out that x-axis, but it also does kind of give me this extra line to deal with if I needed to for a phase shift. It kind of allows for a little bit more freedom with that. Not that I have a phase shift with this example, but again, still, by going every other, it does kind of expand it out so I don't have to draw as many waves. So that's actually kind of more of a, in a way, almost being lazy or just making it so I don't have to do as much of something is really the only line of reasoning behind that. Now, y-axis wise is going to be easier to label again because it's just how far up or down does it go. So I'm just going to count by ones. I don't necessarily have to label every single line. So by me just going to the second and fourth lines and labeling as a 2 and a 4, in both cases positive and negative, at least establishes my scale on the y-axis is I'm counting by ones. Now, as we hopefully paid attention to earlier, the sine and cosine functions are nice every quarter of a period because that would be like I'm going from an x-axis to the y-axis, back to the x-axis, back to the y-axis, and so on and so forth. I'm skipping from quadrant to quadrant, hence why it's a fourth quadrant, again being related to 1/4. In this case, the easiest way to make that happen is just go to the fourth tick mark, so count out 1, 2, 3, 4, and whatever that tick mark is, write down whatever the period is, and that now has kind of forced our scale on the x-axis to be exactly 1/4 of whatever that period is, which again, the whole point of me doing that is so I'm plotting those nice numbers that normally would have been zeros, ones, or negative ones, but because this is being stretched, the ones would actually just turn into 3s because 1 times 3 would stay a 3. But anyway, I'm going to go ahead and just kind of fill in the blanks. If I now know that the fourth one is pi, I should know that the second one is half of that, so pi halves. And if I needed it, the first one here would be pi fourths because that would be half of a half. And if I really needed to continue on, I could figure out the scale here. That last one here, that individual lines here would actually be half of a pi fourth, so that would be like pi eighths. Not that I need that for this one, but again, at least knowing what each value is on a grid, especially when we're creating something that's a little bit odd, at least compared to prior grids that we've dealt with, at least knowing our scale is something that's worth taking note of. Now, when it comes to me and how I would grade these things, I would at least want you to label every other one. Honestly, on your assessments, I'm going to have these already pre-filled out for you, but for your worksheet or your practice, those are going to be completely blank like these 2 examples, so we do need to at least establish the grid by labeling with some numbers and showing that we're counting consistently across the board. It's not like I said that this one, the first one was 1, and then the next one was 5, and then the one after that was 7. Like, you can't change what you count by when it comes down to it, if that makes sense. So here, technically, I'm counting by pi fourths for each tick mark. I'm just only labeling every second one. So technically, I was really just counting by pi halves every 2, and I've established that scale pretty consistently from left to right. So from now, or for now, I should be able to now start putting some of these graphs together, or putting these things on paper here, or on the screen really. But since this was a sine function, I know sine from the unit circle should start at the origin, so there wasn't a shift. That point would stay put, And then now 1/4 of the period later, which is that first tick mark I had, it's going to go to a high point because, again, graphically speaking, I know that it should go towards a positive value if I go in the positive direction for an angle. So 1/4 of the period later, I'm going to go to a high point, and then the only thing I have as an option to do would be to come back down to 0 if we think of the unit circle again. So the next thing in that sequence should be 1/4 of the period later at the x-axis or the midline again, and then after that it would go down to a low spot, so down to a minimum. And notice again, I'm taking advantage of that amplitude being 3 by that's how far I technically went down or up in these cases. And hopefully this is starting to sink in. You can kind of see the pattern. I'm just going to go ahead and continue the rest of the way relatively quick. So far I've gone from a 0 to a high, back to a 0 to a low, back to a 0. So what's next is a high, back to a 0, and then back to a low. And if I followed the other direction, if I was a high and a 0, the one before that must have been a low, and then back to a 0. Now, these are nice and smooth graphs, so instead of us making this really rigid lines, ultimately what we do is we just try and draw a nice smooth curve that goes through all of the points that we just plotted, and it creates our little wave. I'm not going to be that picky. In fact, I was a little bit kind of not so great here, close to the 3 pi halves x-intercept, but at least make it to where you can tell it's rounded. Don't make it like very rigid, in other words. I want hills, not mountains, is a phrase that I often say. So for this one, just make sure that it's nice and smooth because it does kind of follow that circular pattern. It does make nice, smooth transitions from point to point on the unit circle. Even though we're only really recognizing 3 in each quadrant, there technically are a whole bunch of different ratios, and it does cycle through them nice and smooth, hence why it creates this more of a wave, not like a heartbeat sensor when it comes down to it. Now if we go ahead and maybe look at the second example here, hopefully this is kind of coming together. But if we look at the second example, I do have a negative, so that basically is meaning it's going to flip it upside down. So cosine normally should start at a high point, so that basically just tells me I'm actually going to start at a low point. So just kind of take mental note of the first point we're going to plot is a low point, and then from a low point the only thing I could do is go back to a midline or a 0 in this case. Now as far as the labeling of things, I probably need to figure out what my amplitude is. Well, my amplitude is just that number in front, which is a 2. And again, amplitude is a distance, which is why it's a positive 2, not a negative 2. But again, that negative, the only thing we're really thinking of about that is the fact that it makes our graph be upside down. Period in this case is going to be 2 pi divided by that b value. Well, what's a little tricky with fractions, something like that, is I can technically picture this x divided by 4 is really like it's 1/4 multiplying with x. So dividing by 4 is the same as multiplying by 1/4. And then at this point it would be that keep flip change as mentioned earlier, where I would keep the 2 pi, flip the 4 over 1, so that would really just turn into times a 4. And so ultimately my period in this case will be 8 pi. So just like before, I'm going to use every other line on the x-axis, and then y-axis wise with my amplitude being 2, I feel like I can probably just count by ones and call it good. That would fit. If I wanted to go every other line on the y-axis, that still technically would work as well. I could probably make that fit, and I would just have maybe 2 where the 4 is currently. So if I go ahead and maybe make the y-axis scale just be counting by ones, I feel like that makes sense for this example. X-axis, as mentioned before, just go out to the 4th tick mark, so 1, 2, 3, 4. That's going to be the period, which we just found to be 8 pi, which means the second tick mark must be 4 pi, which means technically I'm counting by 2 pi's as I go. But anyway, I'll just go every other one. So this first one here at the far left would be the negative 4 pi, and then after 8 pi that would take me up to 12 pi, and I feel like now, yes, I've established a grid with at least enough numbers that I can see that I'm technically counting by 2 pi's, or each individual line technically was equal to 1 pi. Now, as we mentioned at the beginning here, cosine normally should start at a high point, but because it's been flipped upside down, it's actually going to start at a low point. That low point happens to be whatever the amplitude is, but now negative, so negative 2. And then from there, the only option I have is 1/4 of the period later. It should go back to 0. Doesn't matter if I go to the left or to the right. And now I can kind of see that the pattern is going to follow through with a 0 high, 0 low, 0 high, 0 low type thing. So if I was a low and then a 0, the next one must be a high, back to a 0, back to a low, 0, high, and 0. If I go the other direction, if I was a low and a 0, the one before that must have been a high, so that's as far as I can go left. And now I just draw a nice smooth curve that goes through all of those points. Again, making hills, not mountains. And there we go. We've got two examples of drawing a sine or a cosine graph, one of them having a negative sign. Hopefully you can kind of see how we deal with all those things, but generally speaking, sine should start at the origin, cosine should start at a high or a low, depending on if it has a negative. And then sine also should generally go up from its first point, but if it had a negative, it would just go down to begin. Again, that's all negatives do, is just flip them upside down, so it would just be the opposite direction initially if you saw that there was a negative in front of the function. All right, we'll go ahead and do a couple more examples of sine and cosine. These are going to be more like examples that you would find in the 6.6, not so much 6.5. 6.5 stayed more in the only having amplitude and period changes. 6.6 is actually more what if I had those, but also some shifting. So notice these ones now I have addition and subtraction getting involved. So hopefully this will just kind of solidify like how do I deal with that situation. So to start, good beginning here would just be identify the key parts. So amplitude, period, phase shift, and vertical shift. Those are like the four things I'm looking for. I don't see any negatives, so there aren't no reflections, so everything's going to stay I guess relatively standard, meaning I don't have to think like the reverse direction or anything like that. My amplitude in both of these cases are just going to be whatever number's in front. So for this first one, it's just going to be my amplitude is 2. Period for sine and cosine generally should be 2 pi divided by whatever the b value is. Well, in this case, notice there's actually kind of no number in front of the x, so that means we can apply that to equal 1. So the period for this is actually just going to stay 2 pi. So it has not been shrunk or stretched horizontally, but it did get stretched vertically because the amplitude changed. It was supposed to be a 1, now it's a 2, no big deal. My phase shift, on the other hand, now I'm going to try and take that c value and do its value divided by the b, which in this case was still a 1, so it's really just going to be pi fourths, or it's going to stay pi fourths. And now I'm just going to look at this and go, okay, well that was subtraction inside, so from the past I hopefully remember that subtraction moves it to the right, so I'm just going to kind of account for my phase shift. I'll say what the amount is first, just by doing c divided by b, ignoring any and all negatives, and then look back to do I see a plus or a minus, and answer with either to the right or to the left appropriately. So again, subtraction is right, addition is to the left. And then vertical shift is the easiest of the four probably, or maybe about as easy as the amplitude, I suppose. But this one I just have addition by 1 outside, so I know that means it's being shifted up 1 place, or 1 up. So when it comes to labeling, I'm going to do pretty much the same thing as the last two examples. Use every other line just for sines and cosines. If you want to use every line, go for it. It just will make it so you have to do a few more waves when it comes down to it, because you'd have more points to plot. So to each their own. I'm just kind of trying to give you a general thing, like if we just do the same thing all the time, at least with the x-axis, it should hopefully make the somewhat confusing part of this seem a little bit easier. So now when it comes to labeling the y-axis, I'm just going to look at my amplitude and my vertical shift. My vertical shift was 1, my amplitude was 2, so counting by a 1 vertically, or every other one being 2, I guess is more how I would want to do that, because I don't want to have to label every line. But again, establishing a scale of counting by 1 on the y-axis seems to make sense for both of those two concepts. Horizontally, I'm just going to go to the fourth one, 1, 2, 3, 4, and label with the period like I've done on the last two examples. So 2 pi on that fourth one, which means the first one would be pi, which means this one technically is pi halves. And so what's actually nice by me skipping and going every other one, that actually one single line is equal to pi fourths, which I did need to know for my phase shift to make any sense. Or to even be able to be accomplished, I guess is maybe a better way of me saying that. So I have at least created a grid where I can account for both my phase shift and my period. Period for sure, right? It was the phase shift that I was just kind of fingers crossed hoping that pi fourths was going to fit somehow, some way. It just ends up turning into it's just one line instead of one tick mark. So it still is going to be 2 lines for every quarter of the period, as we kind of skipped every other, so kind of keep that in mind. And technically every second tick mark here is just pi more than the one before, so this would be 3 pi. And now let's go ahead and start plotting some points on our grid. So sine normally should start at the origin, so normally I would have my first point be here dead center, but this one has been shifted up 1, and then it has an amplitude, or sorry, has been also shifted to the right pi 4. So what I'm going to do is, to make these zeros a little easier, is I'm going to try and draw a new midline just using kind of a dashed or a really lightly drawn line, and just know that all my zeros are going to fall on this midline that I kind of drew right there at basically a y equals 1. And that's, again, accounting for that vertical shift. So that's the only thing that really was going to change, at least as far as my zeros were concerned, is they're no longer going to be on the x-axis. They're going to be on that horizontal line at y equals 1. Now, again, let's go ahead and start figuring out where these points should go. So again, if it's supposed to start at the origin, I go up 1 and then to the right pi fourths, which is just one line. So my first point I should plot should be that point right there that you can hopefully see a little bit easier if I highlight it. And now, since this is sine, I just need to think, what should I do from that midline? Well, sine normally should go up unless it's been reflected. It hasn't been reflected, so I know it will go up, and 1/4 of the period happens to be 2 of these lines, so I'm just going to go 2 lines to the right. I know that my amplitude is 2, so I'd go up 2 and place my first high. And at this point now I can start to see that the pattern is going to go, well, if that was 0, then high. 2 later should be back to a 0, back to a low, back to a 0, and a high, and a 0, and a low. And if I continued on, oops, that one was not quite low enough. There we go. If I go the other direction, if I was a high and a 0, before that must have been a low, back to a 0, and if I could fit it, back to a high. So now I can kind of see like my shape of the graph is going to be still a wave, but this time it's not the x-axis cutting it perfectly in half, it's that new kind of midline that I drew initially at y equals 1 that now is going to be the thing that cuts it in half. But as we can see, that first point, once I get that plotted, now all of the other points just kind of fall in line. So we really need to be very mindful of, did I get that first point correct? And then from there, am I going to go the correct direction? So those are kind of the two main things to get the ball rolling. And once you've kind of committed to those, then from there it's just figure out how much 1/4 of your period is, which in this case I made 1/4 of the period equal to 2 of those lines. And so just kind of consistently count, go 2 to the right, that's the next nice number. So either a high, a mid, or a low, depending on where I just was. If we go ahead and look at the second example here, I've got an amplitude, it looks like, of 3, since that's the number in front. I do have a period change here because there is multiplication inside, so it's going to be 2 pi divided by the b value of 4, which reduces to pi halves. I have a phase shift in this case of what looks like c over b would be pi halves divided by 4, which would equal pi eighths. And then I have a vertical shift of 2 down, or you could just call that -2. And the phase shift, because it was addition, I should also probably mention that was to the left pi eighths, just for my own sake. So I know it's going to be pi eighths to the left, or we could call that negative pi eighths, if that helps that way as well. But again, now it just comes down to labeling my axes in an appropriate way that fits the numbers I just found. I'm going to hope that using every other one like I did on the previous one, and just going out to the fourth, 1, 2, 3, 4, and just writing the period of pi halves will work out. If that one's pi halves, this first one here would be pi fourths, because that's half of that. And then half of that would be pi eighths. So yes, I did account for my phase shift this time, and in fact though it was 1 full tick mark instead of just 1 single line like the last example. So in theory a little bit easier, because I won't be going in between like I had last time. I actually will get to just plot on the actual tick marks that I've created. So if I kind of fill out the rest of this, I have pi fourths every 2, so this would be 3 pi fourths for the last one going to the right, and that should be good enough. My amplitude here was 3 with a vertical shift 2 down, so I think counting by ones makes the most sense. So still a 2 and a 4, a -2 and a -4 for those ones. That gets me down to -5, which is as low as I'll need to go, so that's good. Now let's go ahead and just visualize where that new midline is going to be because of the shift down. So I'm going to just draw a dashed line here at y equals -2, or 2 below the x-axis. That's where my zeros or midline points will go. And now let's go ahead and figure out what I should do. Well, cosine normally should start at a high point, so it normally should have started at 3. That would have gotten shifted down 2 places, so that would be now at 1. And then it did say pi eighths to the left, so the first point I should plot should be right there. If you didn't see what I just did, it should be that point that I just highlighted. And again, that should be a high point because cosine has normally started at, or should normally start at a high point unless it's been reflected. I didn't have a negative like the last time I had a cosine, so this does in fact start at a high. So the only option I have from there is 1/4 of the period later, it's going to come back down to that midline. So I know the next 2 points to the left or to the right should be back at the mid, and now I can just go every 1/4 of the period, which again is just 2 lines or 1 tick mark with how I've labeled it. is going to be where the next nice thing is. So if I went high, then 0, the next one must be at a low. Again, taking advantage of my amplitude being 3, so I'm going 3 below that midline, and then back up, and now we can start to see that the graph kind of alternates back and forth between +1 and -5, and then going through a -2 halfway in between there, since that's where my midline was. And I should now be able to just sketch a nice smooth curve that passes through all those points. And voila, we've got our 2 examples of drawing a sine or a cosine graph with all of the possible things being changed: amplitudes, periods, phase shifts, vertical shifts, all sorts of things. Notice the pattern still stays the same. I just need to go 0 high, 0 low, 0 high, 0 low. But really it's all those quote-unquote zeros. Potentially might be higher or lower than the x-axis, just depending on if there was a vertical shift or not. All right, moving on to now the reciprocals, secant and cosecant. What's hopefully going to be nice about this is notice I still have the A, B, C, and D. They're all in the same spot, so I'm not going to go too much in depth with this. Secant and cosecant are just reciprocals of sine and cosine, so really all this information as far as the period, phase shift, vertical shift, those are all still the exact same. I still use 2 pi divided by b, since it is still supposed to be 2 pi normally, unless it's been stretched or shrink. The only thing that's a little bit different is I don't get to use the word amplitude, because now, since it's not a here's how far I can go away, this actually is going to be the how close could I get. So it really doesn't have a special name, but at least knowing what that distance is, notice that still is utilizing the absolute value of a, but that's just going to be something that I'll take advantage of. So honestly, when it comes to drawing the graphs of these, which actually the next slide says here, when it comes to drawing these graphs, we just plot all the points as if it was a secant, or if it was a secant, I'd graph all the points for a cosine, or if it was cosecant, I would graph all the points for a sine, the same way I would have just with the last 4 examples. However, it's what I do with each of those points that's going to be different. Instead of drawing a wave, I actually will put vertical asymptotes at all the zeros, and then I'll make either U's or upside down U's, as mentioned earlier in the video, at either the high points or the low points appropriately, making sure that I'm going away from the midline. I never actually cross over the midline with these ones. All right, so let's go ahead and just try a couple of examples here. Hopefully you can kind of see that the pattern here. I'm just going to do one without any shifts, one with. But I hope you can kind of see just the similarities between. I do everything the same for sine and cosine, so if I know how to do those, there's really no reason I shouldn't be able to do these. It's just a matter of like how the graph looks in the end that will be obviously a little bit different. So for this first example, I've got 2 times secant, so that basically means I need to think of the cosine graph, since that is the reciprocal of secant is cosine, and just think in terms of what would my a value be. Well, the a value is the 2, and then I know that the period for this one, since there is a b value, it's going to be 2 pi divided by that number that's in front of x. So dividing by 2 is really like the same as multiplying by 1/2, and if I divide 2 by 1/2, that would be same as doing 2 pi times the reciprocal of 1/2, which is 2, and that would turn into 4 pi. So just like before, I'm going to use every other line on the x-axis. Hopefully we're seeing a very similar pattern here. I'm going to go to the 4th tick mark and label with the period, which was 4 pi from what I just found, which means the second one should be 2 pi, and now label every other one with 2 pi more, so that means 6 pi, and voila, we've got our x-axis labeled pretty quick. Vertically on the y-axis here, I'm going to go ahead and just count by ones as per usual. Since the a value was just a 2, that seems logical to me. If we wanted to, we could count by 2s. It would just make them a little bit closer to the midline. No big deal, but here again, I just needed to make sure I could fit everything on this grid. Now, since this is a cosine graph we're thinking of, I'm just going to think of all of the points that I would normally plot for that. So normally cosine should start at a high point. It hasn't been shifted at all, so I know that's going to stay the high point. And then from there, just going to the left, it must go then a mid followed by a low. And going to the right, it would go a mid to a low as well, but then back to a mid, back to a high, back to a mid, back to a low, back to a mid. And again, notice all my highs and lows were a distance 2 away from the midline, because again, the a value, which would have been called the amplitude for cosine, was 2. Now here's where normally if this was a cosine, I would actually draw the wave through those points, and that's why things are now slightly different. I'm doing a secant graph, so I'm actually going to make vertical asymptotes at all of the quote-unquote midlines or zeros. And so if I go ahead and draw those in there, notice those are going to be things that don't cross over. And now I just draw U's at all of the highs. So I'll go ahead and just knock those ones out. Looks like I can only fit 2 of those here. And then upside down U's on all of the lows. So kind of only half of one can fit on the grid with that first one, but now I've got two full ones here. And voila, we've got our first secant graph, where notice it really wasn't a whole lot more difficult. It's the same approach as sine and cosine. It just was a matter of like how I interpreted the points I plotted that now was different. So I kind of flipped that wave inside out. If it helps, you can kind of picture like, okay, there was technically a cosine graph here drawn in the middle, right? But I'm keeping that part out. So if I go ahead and just get rid of that again, notice I still have that graph for the secant, and then the graph is what I have there. I don't need the extra stuff on the inside. If you happen to draw the sine or cosine graph in the middle, please, please, please just try and make it as light as possible with a pencil, so you don't accidentally try and answer a secant graph with a cosine graph and kind of confuse me when it comes to grading. I want you to at least recognize or demonstrate for me that you understand that the secant graph truly is the parts that I currently have on the screen, not the actual wave that's in the middle. But if the wave in the middle helps you somehow, some way, go ahead and sketch it. Just make sure that you are very, very light with that, or just make your actual graph for the secant really, really dark in comparison. I don't know what best strategy will work for you, but again, kind of just think in terms of what am I trying to show that I understand. Here in this case, I want to make sure that you're showing you understand that it should be the U's and upside down U's for this secant graph. Similarly speaking, here with the second example, we're going to go ahead and identify all the parts. Here now I just have some shifts that I have to account for. So this has the A value of 3, so that's going to be like the amplitude for this. It is a cosecant graph, so I need to think of all the points for sine generally. My period looks like is just going to be 2 pi divided by 1, so 2 pi. I have a phase shift for this one that would just be pi halves divided by 1, which stays pi halves, but because it's addition, that's going to be specifically to the left. And then I do have a vertical shift as well because of the subtraction by 1, so that's going to be 1 down from normal. So if I now start labeling my axes, again using every other one on the x-axis is a good general approach for all sines, cosines, secants, and cosecants. Let's see, an A of 3 with a vertical shift of 1, counting by 1s on the y-axis seems like it's going to be a good idea as well. So that hasn't really changed a whole lot from problem to problem, but let's say this was counting by or had a vertical shift of 10 and an amplitude of 30. I'd maybe want to just count by 10s instead of 1s, but I think that would be a relatively easy transition for any of you to make. Horizontally, again, we're just going to go to the 4th tick mark, 1, 2, 3, 4, and write down whatever the period was, which we found to be 2 pi, which means the first one's pi, which means 1 tick mark is pi halves. So yes, my grid does account for the pi halves that I identified phase shift-wise. And now I'm going to go ahead and just label at least every other one, pi, 2 pi, so this was 3 pi, and voila, we've got a scale established, everything labeled as good as can be. So now let's start plotting some points. Again, we're going to plot points for sine, since this is a cosecant function. And sine normally should start at the origin, but because of the phase shift and vertical shift, it's actually going to have to move. So I'm going to go ahead and just draw that midline down 1, so I know all my mid points or zeros will actually be at -1 instead of the x-axis. I know it's going to be pi halves left, which was 1 tick mark, so my first point that I'm going to plot is actually down here in like the 3rd quadrant. Now from there it's going to go up to a high point, generally speaking. I don't see a negative, so that stays true for sine, at least this specific one. So I'm going to go up 3 a quarter of the period later, so 1 tick mark over, or the not x-axis, but y-axis. I'm going to go up 3 from the midline, 1, 2, 3, so that takes me to a value of 2. And then the next thing should be back to a mid, then back to a low, so 1, 2, 3 below, takes me down to -4, and then back to the mid, and then a high. So I'm going to keep just bouncing back and forth between what looks like 2, -1, and -4, and just keep plotting the points every quarter of a period away from each other. And then again, instead of me drawing the wave like I normally would for a sine graph, I'm now actually just going to interpret where the zeros were. That's going to be vertical asymptotes. Get all those on the screen, and now all the high points to draw U-shapes on, making sure again not to cross over those vertical asymptotes, and then all of the other parts draw upside down U's, so these ones barely fit on there. No big deal, we still are getting our point across that it does in fact kind of leave that extra dead space here in the middle. That's where the sine graph would have been drawn if I did actually want to. But anytime, like if you notice that we've maybe drawn our U-shape's going this way. If you ever cross over that midline, that's a good indicator of, oops, I put an upside down U when I should have put a right side up U. It should, again, kind of leave that open space where a sine or cosine graph would have existed. So again, it always has to go away from the midline just to kind of hammer that point home. Okay, and next we'll talk about the tangent and cotangent. So notice again, we still have the same general spaces for where A, B, C, and D would be. A being anything that affects something in the graph vertically by stretching or shrinking, depending on its value. B being something that stretches the period or shortens the period, depending on how big or small that number is. Adding inside becoming like a horizontal shift or phase shift, and then adding outside, or potentially subtracting in both those cases as well, I suppose. But subtracting or adding outside would be a vertical shift. So again, all the same general setup, but now because we're talking about tangent and cotangent, remember the period right now has to be slightly different. In this case, the period, instead of being 2 pi generally, it now should just be 1 pi, and I would just then do the same thing with b. I just divide by whatever that b value is, and that should tell me how long it takes to repeat. Now when it comes to the actual plotting of points for either a tangent or a cotangent, tangent graph, generally speaking, should come up the page, whereas a cotangent should generally come down the page. Only exceptions to that would be if there was a negative sign, it might flip it to where it goes the opposite direction, so always kind of pay attention to, do I have any negatives? But generally, again, tangent should come up the page, tangent should come down the page, and instead of us following a pattern like the sine and cosine graphs where I go like 0 high, 0 low, 0 high, 0 low, this actually is going to be, let's plot all of the same things and take advantage of like halfway between stuff is always consistently going to be something, and we'll kind of utilize the unit circle as we go through. So I know there's a whole bunch of info on the screen right here. I'll try and summarize it. Ultimately, when it comes to graphing tangent, since it starts at 0 on the unit circle, we'll actually just plot all of the zeros, just making sure that all of the zeros are separated by whatever I found the period to be. So if the period was, say, 20 pi, I'd plot my first 0 at the origin, then the next one be over 20 pi, plot the next, and then the next one 40 pi, then 60 pi, and so on and so forth. And then halfway between each 0 will always be vertical asymptotes. And similarly, we can go the other way. If I had vertical asymptotes plotted, halfway between them would have to be zeros. And then in between each of those, it's either going to go up whatever the a value is or down whatever the a value is. So that's again where tangent, knowing that its shape should come up the page. If we have our 0, when I go to the right a little bit, I know I should go up. If I go to the left a little bit, I should go down. And whatever that amount is should always be whatever a happens to equal. Now, if it had a negative in front, I would just completely flip that on its head. And instead of going down and to the left, I'd go up and to the left and make sure that I just did a perfect opposite. So that's all a negative would do to a graph. Cotangent, on the other hand, should always be decreasing. So as mentioned before, it should come down the page for that. But instead of me plotting all of the zeros to start, I actually would figure out, since tangent is 0, that would become undefined if I found its reciprocal. So actually, I would draw all of the asymptotes first, and then take advantage of, again, halfway between asymptotes or zeros, and then halfway between zeros and asymptotes should be either up a or down whatever a is. Again, just making sure that it's making the correct shape, or at least going this correct direction for that shape, whether it's a tangent or a cotangent. And again, hopefully this will all kind of come together as you see examples get worked through. We'll start with one that's relatively easy, and then another one that has a little bit of shifting going on, just like we did with the sines, cosines, secants, and cosecants. So, first example here, let's go ahead and work through. We can see that the first one here is a tangent, so I know that the shape of this should come up the page from left to right. I can see that the a value is just going to be a 1, since that's the number in front of tangent, or if I don't see a number, it would be implied to be 1 in that spot. The period happens to be changing. In this case, the period would be pi divided by that b value, so in this case being a 2 would be pi halves. And now I'll go ahead and take advantage of whatever that is in each of those cases as to how I'm going to label either my x-axis or y-axis. So for this specific example, or for tangents, it actually, oddly enough, is better to utilize every single line instead of expanding it out like we did with the sine and cosine graphs. And it's more just generally so it looks more natural. I don't know if that's going to make sense to you or whatnot, but maybe as we draw these, you'll kind of see like, oh yeah, that would look a little bit weird if I stretched it out horizontally. So again, generally speaking, for tangent and cotangent, use every line, whereas all the other functions go every other line for at least the grids I provide to you guys. Again, on the test that you guys will have for this, or any assessment, you're going to end up having these already pre-labeled for you, but in the homework, again, I have you kind of challenged a little bit by having to create your own scale. So vertically here, since my A value was just a 1, I'm just going to count by ones. Seems logical, just like I've done almost every other time. Horizontally, I'm still going to do the same general thing of let's go every 4th tick mark. That way I kind of take advantage of every quarter of the period. It's actually a nice thing. It's just whether it's a 0, an undefined value, or a 1 or a -1. So if I go out 1, 2, 3, 4, it's going to be at pi halves. And then I'm just going to basically label every 4th ones. Otherwise, it's going to get super jumbled. So negative pi halves over here. If that one was pi halves, 1, 2, 3, 4 later, there would be 2 pi halves, which is really pi. And then 1, 2, 3, 4 again, that would be now 3 pi halves. And I feel like I've at least established a grid well enough that I can make these plots happen. So now from here, I'm going to go ahead and start plotting some of the points. I know tangent should normally be 0 to start, so I'm going to plot that first point at 0. And instead of me like following some pattern, I'm just going to say, well, a full period away, which is pi halves, it should be the same thing. So I'm just going to plot all of the zeros 4 lines away from each other because, well, that's what I made my grid worth. Every 4 lines was exactly supposed to be 1 period. And as mentioned before, halfway between all of those zeros that I've just plotted should be vertical asymptotes or undefined values. So I'm just going to go ahead and just start drawing those vertical asymptotes in between. Now it comes down to halfway between each of those things. So halfway between a 0 and an asymptote, I'm either going to go up A or down A. And again, that's what goes back to like, okay, the shape of the graph was supposed to go up the page. So if I'm at this first 0 at the origin, that means I should go up and to the right. And my A value was 1, so I'm going to go up 1 and then halfway. So that should be that point right there, which then means the other direction, I must go down 1 and over to that halfway point. And it creates that little thing. So my first one, if we wanted to see what it looks like right now, should now create that cubic that, again, did come up the page. So that's what was supposed to happen for tangent, as we talked about before we even started. And now I've got some nice points. Now I just repeat that same process in between each one of these. So you can kind of picture this like, it's almost like I'm drawing 3 points that have the same slope as whatever A is. Since A is +1, it makes a +1 slope through there. And now I just take advantage of, once I have those points, I should be able to just draw those kind of cubic shapes where I start close to the vertical asymptote, pass through the 3, and finish close to the other or next vertical asymptote. Technically, I guess I can fit half of one over here on the far left. And there we go. We've got our first tangent example now plotted. So cotangent, when we look at this second example, it's not going to be a whole lot different other than instead of plotting zeros to start, since it is the reciprocal of tangent, I'll actually just plot them as undefined. Because after all, we've mentioned this probably 2 or 3 times now in the video, anytime you take 0 and flip it or become its reciprocal, it would have to become an undefined value. So I actually, again, just plot the vertical asymptotes for cotangent first, and then halfway between get the zeros, and then halfway between that go either up A or down A. So here the A value is 2, so it's going to be a little bit different than the last example. It'll be kind of vertically stretched or a little bit steeper. My period here is actually just going to be pi divided by 1. So again, it's just taking advantage of pi divided by b. So pi is really the value for this since there wasn't a number in front of x. I do have a phase shift for this one of pi halves. And it's specifically because of subtraction going to be to the right. And then I did have a vertical shift with this one as well, which subtracting 1 is just going to mean it moves it down 1 place. So if I now start labeling my axes, again, usually with tangent and cotangent, it's best to use every line instead of every other. And it would be okay if you wanted to go every other. There's nothing wrong with that. It just, again, you'll have fewer examples or fewer of the cycles being shown, but it also would kind of stretch itself out, so it would look really weird, kind of like that, if that makes any sense to you. So again, that's kind of why we would use every one. For this one, let's see, my A value is 2, so I think just counting by ones, just like I have always been doing. I didn't get very creative, I guess, with my A values in this video, but my vertical axis here, again, just counting by ones seems logical for a value of 2. I do have a shift down 1, so that accounts for both of those relatively easy. Let's see, I go out to the 4th tick mark, 1, 2, 3, 4, call that pi, which means the second one is pi halves, so I can account for phase shift pi halves. It's just going to be shift to the right 2 places, so actually where I just wrote pi halves. I don't need to label every other one, I'll just go every 4th, so if I'm counting by pi, let's see, 1, 2, 3, 4 later, that's going to be 2 pi. 1, 2, 3, 4 later, that's going to be 3 pi. And there we go. I've put enough on there. I've established I'm counting technically by pi fourths. Now let's go ahead and start plotting some things down here. I do have a horizontal shift or phase shift of pi halves. I have a vertical shift of 1 down. So I'm going to go ahead and just do kind of that idea that we did with sine and cosine and secant and cosecant. Anytime I have a vertical shift, just kind of draw like a new midline, if you will. That's going to be where the quote-unquote zeros will go. Since it was shifted down 1, it's just going to be at -1. And now let's go with the, normally it should be an undefined value, so it should be a vertical asymptote to start. Shifting that down wouldn't really change it a whole lot. It would still be at the y-axis, but then the pi halves to the right actually does change that. Now, ultimately, I've made it every 4 lines is the same thing as a period, so I'm just going to go 1, 2, 3, 4 lines later and draw the same thing since it is periodic. So every 4 lines now, 1, 2, 3, 4, it's going to be another vertical asymptote until I run out of grid going each direction. So if I now go backwards, 1, 2, 3, 4, I've got my last vertical asymptote I can really fit on here right there. And so I've got that taken care of. Now halfway in between should be just zeros. I just know that the zeros should be down at -1. So I actually have my first 0 go here. And if I just continue halfway in between each of those vertical asymptotes, plotting those zeros, we've got everything there. And now I know cotangent, generally speaking, should come down the page. So that means halfway in between the zeros and vertical asymptotes, instead of me going up and down 1, I'm actually going to go up and down 2. So if I want it to come down the page, when I go to the left of this first 0, it should be above. When I go to the right, it should be below. And notice again, I took advantage of that distance here was 2. So I went 2 above or below that midline. And now at this point, we can kind of see that first cycle of 1 is going to be kind of stretched out vertically a little bit compared to the previous example. But it does definitely still come down the page. And now we just kind of follow that same pattern in between, 2 above and 2 below and the halfway points. And now once I have them, I can just start close to one asymptote, finish close to the next one, and pass through those 3 points accordingly, making sure, again, I'm making the same shape in between each one of these, because after all, it is a periodic function. They should look identical. And voila, we've got now hopefully our tangent and cotangent figured out. Again, one of the biggest differences between the two when it comes to at least the analysis is the period now is pi divided by b instead of 2 pi like it has been for the other 4. So just anything that has the word tangent involved, just remember that's going to use pi. Everything else uses 2 pi. All right, so now on to the last couple of examples. This how maybe could I work backwards from a graph? We'll just maybe only worry about working backwards from like a graph of either sine or cosine. The ability to be able to do this, ultimately what we would do is just identify some of the key parts from each graph. So we could look at each one of these and go, what's the amplitude, what's the period? If I go ahead and just kind of mark on each of these what the period would look like, it would be how far those things are separated from each other. So ultimately I'll just take advantage of how far each of those are and just maybe kind of group these up. So I can hopefully easily, oops, that one was off a little bit, easily identify which one has which period, or maybe which one has which b value for each one of these. And then we can also identify the a values pretty quick. It looks like these last two are the only ones that go a little bit different. So it seems like the ABC, like basically A through G, all of those here, I know those letters are kind of small to see, but A through G, all of those look like they have an amplitude of 2. So if all of those have some amplitude of 2, ultimately from there I can kind of narrow down. Looks like there's only a couple that have a different amplitude down here at the bottom. There's only this one here and this one here that have an amplitude, it looks like, of 3. So that kind of tells me one of these last two, H and I, must be those two that have either a 3 or a -3. So what we could do maybe visually here is just kind of look at what makes the most sense. Anything that starts at a high point or a low point must be a cosine graph. So this first one we could just say, well, I know that one's going to be cosine because it starts at a positive. B must be a sine since it starts at 0. C, it starts at a low, so that must be an opposite of cosine or an upside down cosine, so negative cosine. Next one, it looks like it started at the origin but go down to begin, so that one looks like a negative sine. And you can just kind of narrow down out of the choices we have underneath here which one makes the most sense for each of these grids. But we can kind of tell, again, the last one here, it looks like if I continue going on, that's a negative cosine since it starts at a low. Then it starts at a 0 here, so it's a sign, but then goes down, so it must be negative sign. And then the last one would be a positive cosine because, again, it's starting at a high point. So if I now start looking for what things do I have in common, well, I kind of can do the two that have an amplitude of 3, which were h and I. Whichever one I just said was supposed to be a cosine that's positive, that must be the I, which then means the negative 3 times sine, that must be the h. So I've already got 2 of those knocked out, so I don't need to worry about those 2 anymore. Now from here it would be, let's look at what our periods are. So the period for each of these that have 4 pi as that last thing, that would be 4 pi as the period. So if I just think, okay, well, if my period is equal to 2 pi divided by b for sines and cosines, I don't know why I just wrote 2, my bad, 2 pi divided by b. If I really wanted to, I could solve for b just by multiplying both sides by b and then dividing by whatever that period was. And if I kind of think in terms of what should that kind of shortcut be to identify the b value, well, ultimately I just kind of identified here that b must equal 2 pi or divided by whatever that period is. So if I did that for all these examples that have 4 pi involved, that kind of tells me that the b should be, for that case, 2 pi divided by 4 pi, which would equal a regular 1/2. So all the ones that have 4 pi, which looks like A, B, C, and D, all should have a b value of 1/2. So we could start going through and identifying, okay, these all have a b of 1/2, whereas the ones that don't have 4 pi, they just have regular 4. If I did that here, now it's going to be b equals 2 pi just divided by 4, not 4 pi. That actually now reduces to pi halves. So those are the ones that, if we look down at the bottom, notice some of them had pi halves x, whereas others just had 1/2 x, or maybe just an x over a 2. So that kind of helps narrow it down as well. But from here, now let's just identify which ones have the correct sign and correct function. If we look at this first example, 2 times sine, I look for a positive sign. It does have pi halves in front, so that means I should have the one with a period of 4. So which one had a positive sign and period of 4? That looks like it would be letter F. If I go with the next one, positive 2 with cosine and then also pi halves, so that means I should just have a regular 4 that it's going through instead of 4 pi. Which one was a positive cosine? That looks like the one right before E. 2 cosine of 1/2 x, so this is one that should go through 4 pi as the period. So that would be something where I said it was positive cosine. That looks like it must be positive A, or not positive A, but letter A. Skipping ahead, now I've got 2 sine of 1/2 x, so that's going to be which one is a positive sine. That also goes through 4 pi, so that looks like that was B. Next one, negative 2 cosine, also going through 4 pi, so that would be whichever one is negative cosine, which we said just a second ago was C. Negative 2 cosine with pi halves, that means it goes through 4, so which one's negative cosine with 4G? And that kind of leaves me, there's only one option left, but let's just go ahead and look at it a little bit more specifically. It is 1/2 x, so that should go through 4 pi as its period. So since that one is negative 2 sine, that must be letter D, which was the last option I had altogether anyway. Alright, so last examples are what if I didn't give you a visual and I still wanted you to just come up with what the equation could be. Ultimately with these, if I'm not telling you whether it's been flipped upside down or not, I don't know if it's going to be a positive A value or a negative A value. So with each of these, I would just go ahead and say if I told you the amplitude was 2, that means the A could have been a positive or a negative 2. So similar with the second one here, I could say that if the amplitude is 3, I know A was either a positive 3 or a negative 3. So we can just group that together and make it a plus or minus symbol. Now the period, right, that should help me identify the B. And as we kind of just came up with, a shortcut for that would just be 2 pi divided by whatever the period was, should give me that B value. So in this case, the B value would be a 2. The second one here would be our B value should equal 2 pi divided by 4 pi, since that's the period. And the pi's cancel, leaving me at 2 over 4, which reduces to 1/2. Phase shift is a little bit tricky. Phase shift is the C value divided by the B value, and then I just need to think in terms of if it says to the right, I know I would have subtraction inside. If it says to the left, I know I'm going to add on the inside. So if I needed to, I could go ahead and take advantage of that, but I kind of have to solve for whatever the b value is first to be able to get it. And if we think in terms of if c over b is equal to the phase shift, all I have to really do to get c by itself is just multiply by the b. So in this case, my phase shift for this is going to be c should equal the 1/2, but then multiplied by the b I found, which was 2, so the c value for this one actually equals 1. If I do the same thing with this one, the c value should equal the b value, which was 1/2, multiplied by the number I'm phase shifting, so in this case pi, so it looks like the c value for this one actually is pi halves. And then the vertical shift down 1, that really should just help me identify the d values. So down 1 means that d must be -1. If there was no vertical shift, that just basically means there would be a 0 in that spot. So it's like I can really just not worry about putting a +0 at the end. So now each of these, if we collect things together, it did say this one wanted to be a sine function according to the problem. So it would just be y equals the ±2 that could have been the a times sine of whatever the b value is I found was 2 goes in front of the x. I did say it was shifted to the right, so that would be subtraction by, and then whatever the c value was, which we found to be 1. And then the vertical shift was -1, and voila. It was mainly, once I had what the values of the letters were, it was just make sure I remember where they go. So a is in front, b is in front of x, c is either added or subtracted to the x, and then the d is always added or subtracted outside of the parentheses. We go ahead and do the same thing with the second one. This time it wants it to be a cosine function. So I'm going to start with the a value ±3 because it could be positive or negative. I know the function was cosine from the problem. It said that b would be 1/2, or we found it to be 1/2 times x. Then I found my phase shift to be left pi, so that would be add pi halves, since that was the value of c that we found. And then +0 at the end, so I could technically just drop the +0 and call it good with that. So I know this was just an epically long video. Hopefully it was still helpful with those that maybe needed to have at least a little extra help or have an extra example from whatever maybe you heard in class, or maybe if you missed it altogether. I'm hoping this is helping you at least have something to work with. But as always, if you have questions, please come find me, let me help. But yeah, again, appreciate you taking any time that you might have put in watching this video, and we'll catch you next time.